Hello everyone. Today we will talk about structural alignment of proteins. So previously we have learned about different types of alignments for example, sequences. We use it for pairwise and multiple alignment, and also we talked about sequence with a profile. And now we are talking about structural alignment of proteins, which is about comparing two proteins structures together. It's not related to the sequences anymore. We are dealing with coordinates of atoms inside proteins. We will talk about it in details about the algorithm because in the previous two sessions we focused on biological context. But today we will see algorithms, and at least for one of them we will go in more details and we practice with that one as an example. So generally there are different types of structural alignment algorithms for proteins. One of them is using RMSD, and we will practice with this one because it's very easy to deal with that manually and practice with that one. But with the rest of them, we need softwares. And in the course syllabus, we are not dealing with the specific softwares. That's why I just mentioned about Dali method, which is a famous one, by using distance matrix alignment. And also, there are other methods, of course, there are so many of them. One of them which I want to mention is LOCK, which uses secondary structures. And you know, for secondary structures, again, we are dealing somehow with sequences. And it's somehow converting everything in terms of secondary structures, and based on them try to predict the function of a protein. This one is also very interesting. Now let's talk about Dali method. Based on the fact that similar 3D structures have similar intramolecular distances. This is based on that. It means that if we have a structure, let's say we have a protein structures like this, and you can find pretty similar one to this one, then you would say, okay, then the distance between, for example, this point of this part of the protein and this one, if I compare it with another structure and this is pretty close, again, I find the atoms and I say, yes, they are close, then in that case, most probably the structure should be the same. And I do it for many points, as much as possible, you see? So that's the idea behind it. So using distance metrics in order to see whether the structures are similar to each other or not. So we are converting everything to two-dimensional case because we are dealing with matrices now, and we are talking about the distance of 2 points. Doesn't matter whether, for example, this is a 3D structure or not. We are just talking about the distance of 2 points, okay? It means that it has a value and it has two variables. So at the end, I will have two-dimensional case. It means that I will have a table like a distance matrix that we practiced before. So in distance matrix, you will have some rows and some columns, you see? And each one of the cells contain a distance. That's why it doesn't matter that the structure is 3D. At the end, you will have a 2D table as a distance matrix. And what do we do here in Dali method? It compares each matrix with another one by sliding vertically or horizontally. I will talk about it and I will show you. And what happens in actual implementation? Each matrix breaks to sub-matrices of fixed size. So let me show you in a very simple example. or in general, I can show you what's happening here. So as I said, you will have a distance matrix, and each one of the cells contains distances. And when I say D1, for example, D1 is equal to the, let's say, specific entity and another one. Okay, so you have such a distance matrix. Let's say it continues. Here I have maybe 20 and so on. So you have such a distance matrix for one protein, and you have also a distance matrix for another protein. Okay, so you have another one here. Let's call it D1 prime, D2 prime, and so on. And you continue also, you fill the table for all of them for the second protein. So what's the Dali method? In this case, you are considering sub-matrices from this big matrix. For example, let's say I consider only this part. Okay, then I compare this part with the whole matrix. How is it working? It means that first I consider these three cells, then these three, then maybe these three. So you see, I'm just sliding this one over this new matrix. Okay, that's what we are doing to try to find the similar path. This is actually the same way we were doing related to local alignment as well. Even for global alignment, we were just moving the sequence and put gaps in order to find the similarities. So it's basically the same logic. And that's what Dali does. And what we are talking about the sub-matrices now, you understand what's happening in actual implementation, as I mentioned. So as you can see, this one could be very time consuming to find. That's why we need a software to do that. Manually, it takes lots of time. That's why I won't ask you about Dali method in the final exam. But with this one, this method is very easy. We call it root mean square deviation. This one is not just used for bioinformatics. It has various applications, but we use it as a tool for bioinformatics in order to find the average distances between atoms in proteins. So when we say what is RMSD in bioinformatics, is the measure of the average distance between the atoms of proteins. Okay, and here we have this term, angstrom, or in German, they call it angstrom. So what does it mean? It means that 1 over 10 million meter. It's very small unit for length. And as we are talking about very small particles and very close lengths, distances, that's why we need such a unit. So when we talk about this unit, you can also show it by A and one circle over it. Or you can show it capital A, one circle over it, okay? Angstrom. And here for RMSD, you can use this formula. So this could be one protein, this one another, V and W. N is the number of atoms that we are comparing with each other. I will show in one example how you can decide it very easily. And here you see, for distance, we use double lines. It means that inside it, we are dealing with vectors. In order to convert it to just elements by elements case, it means that we consider each one of these atoms inside this protein as three-dimensional. It means that each one of them has X, Y, and Z. So you can easily convert it to this one and say, okay, I consider X by X, Y by Y, and Z by Z. It's like comparing one atom coordinates for x1, x2, x3, one vector, and you compare it with another one inside another protein structure. So you could call it, for example, y1, y2, y3. So you are comparing, that's why x1 with y1, x2 with y2, and so on, okay? Or you can write it like x1, y1, z1, in order not to confuse it with the coordinates that we are talking about. And here x2, y2, z2. It's up to you that how you want to write them, okay? We are comparing, for example, these two together. So here inside the formula, we are trying to find the summation of the distances between each coordinates. It means that you find the distance of these two, then distance of these two, and each one of them are powered by 2. At the end, we need a positive solution, right? Because we are talking about the distances. We don't have negative distance. If it is 0 at the end, it means that both proteins are exactly the same in terms of structure. Or as usual, when it happens, it means that we are talking about the same protein, because we don't see exactly the same coordinates for two different proteins. So that's the reason we are powering each one of them by 2, and at the end get the root of that, so that it makes sense in terms of unit. In the statistics, we do the same about variance and standard deviation. Root mean square deviation is based on the statistical method. That's why you see such logic when it comes to distances, and you see the mathematical background behind it. So the formula is pretty easy, and I will show you in example how it works exactly. Now, you see, when we are comparing the structure of two proteins together, you can find RMSD, so that at the end you will find just the positive number for this parameter, and also you can compare them using the primary structure and find the similarity in terms of percentage. Both of these measures are important, because sometimes it happens that proteins happens to be very similar in terms of structure, but their primary structure is not that much higher, like this one. So it just has 15% similarity, but you can see the structures are pretty same. But in another case, you could see, for example, sometimes very high similarity between primary structures, but the 3D structures are very different from one another. That's why both of them are very important in order to give us ideas what's going on. And I cannot say, for example, which one is more important. It's not correct to say that. Both of them is necessary. But anyway, when we are talking about RMSD method, it means that we are not even considering primary structure, and based on just the distance that you will find, you will just interpret that which proteins are similar to each other. We don't even consider primary structure, but as I said, in practice, we need that. We need both of them. What are the pitfalls of RMSD? All atoms are treated equally. This is a big disadvantage. It means that when you are just comparing coordinates with each other, for example, this one belongs to one protein, this one to another, then assume that they are on 3D structure, not 2D as you see on your monitor. So I don't care what's the atom in RMSD method, when I compare this one with this one, we don't know exactly which type of atom is that. Is it nitrogen? Is it hydrogen? We don't know. So that's a big disadvantage of that. And best alignment doesn't always mean minimal RMSD. And that's the same reason I told you here. Maybe you will find similar, a very low number for RMSD, which is good, but unfortunately the primary structures are not the same. And maybe the function of these two proteins are not as similar as we think based on the 3D shape of them. So that's also another disadvantage of this one, but to be fair, most of the structural alignment have this disadvantage anyway. Right, let's see another example that how we compare proteins using the mentioned method. So you simply find the distance between them using that method, and you compare them together. Like, I want to see which protein is similar to this one in terms of structure. So I compare it with another protein. If I have the information related to coordinates of their atoms, which I have through the data bank, then in that case, I can just use this method in order to compare them. So based on this method, if I find these values, then I understand that these two proteins should be more similar to each other, because this one is the minimum value comparing to 3.6. So that's how we use this method and interpret the final answer. Now let's go through the example. I tried to go through a little details, and then in the weekly assignments, we will practice it together. So I want to make your job a little easier for the weekly assignment as much as possible. Then the rest is on you. So as you know, I won't be strict about the weekly assignments. If you make errors, it's okay. You should be careful about the final exam, because even miscalculation decreases points. And this is the format of homework exam. Actually, I'm not that much happy about it, to be strict about, for example, calculations. But during pandemic, unfortunately, we are limited to these types of exams. And hopefully when face-to-face classes will start, we will have totally different types of questions. But anyway, we are just trying to go through this pandemic, and I also try to make everything as simple as possible. Now, let's see, for example, about this a specific method, that how we can deal with it for the weekly assignment, and later I will talk about the final exam. So assume that we want to compare 3 different protein structures based on the coordinates of their atoms using RMSD. So I have coordinates of 3 different proteins, protein 1, protein 2, and protein 3. Now 2 by 2, I should compare them together. It's not possible to compare all of them at once. So it means that I should compare P1 with P2, P1 with P3, and P2 with P3. This one is different from this example that I mentioned, because my goal here was just to compare this specific protein with others. But in this example, we are trying to compare all of them together to understand which pair is more similar, okay? So I have 3 cases that I should compare them together. This example is very easy because it has only 2 atoms inside it. Usually we have much more than that. So this is just a practice to see how it works, and in the exam the number of them are also limited also. And let's practice to see how it works. So for each one of the atoms, you have X, Y, and Z corresponding values of that. You see, for example, for the first one, in the first protein, you have these values. Now again, we should use this formula. So I can write RMSD. I'm comparing first protein with the second one. So we should be careful about how we are assigning values to that, so that we understand how it is related to our example, because this is the general formula, the main formula that we are using. This is the way we should write the formula in order to use it in our solution. So here, what I'm doing, I can use this one directly, because you know this one is the vector type, and I can use this one directly. So I'm calculating the root of 1 over, okay, what is n here? N is 2, because I have only 2 atoms. So you see, for all of the proteins, we will give you exactly the same number. So 1 over 2. Here, I will have I from 1 to 2. Okay, so the rest, now I have I have A and B and C here, instead of, for example, saying about the main protein name. So what I can say here is A, I, because here I goes from 1 to 2. And here we can say, for example, X minus, now I want to compare protein 1 with protein 2. So here I have B instead of A. So B, I, X. But here also we should be careful to include all of them in terms of Y and so on. So power 2 plus this one continues. So let me show you on this one. So from the beginning, 1 over 2, I will have I from 1 to 2. I will have A, I, X minus B, I, X power 2. I will put another parenthesis here so that you understand this is related to this summation. Plus, then I write for the rest of them in terms of Y and Z. Minus B, I, Y, 2. This one continues actually. Plus I, Z minus B, I, Z power 2. This is extra, you can erase that. Okay, so one by one, I should just assign the values to that. So how do you assign the value? For example, for the first one, let's say 1, 2. Now I want to apply the summation, okay? So it means that I consider A1 X minus B1 X power 2. You continue and do the same for this part and this part. Okay, so instead of I, you will put 1, and then you will consider A2 X. They are indices, okay? Both of them are indices, not multiplication for A. And B2 X power 2, and continue it until A2Z minus B2Z power 2. So one by one, you can assign the number. In the exam, of course, you will write all of them to show all the parts. But for now, let me just practice it with some examples so that you see how you can read it from the elements inside the information that you have here. So for example, A1x, what's the value of that? This part is A1, this one is x, so the intersection is 23. That's how you read the number. For example, what is A2z? So A2z is this one, right? The intersection between A2 and z. For example, what is C2y? Okay, this is C2, this is y, so the intersection of them is 5. So this is how you assign the values in them. And at the end, what you find is a positive number, or in very specific case, 0, which almost never happens. Otherwise, they are exactly the same proteins. So we should be careful. If you find negative values at the end, it means that you did some miscalculations. We are powering everything by 2. Here, for real numbers, you cannot find an answer which is negative under the square root. So obviously, the final answer here should be positive. Okay, guys, we will practice with it also in the weekly assignment. And in the final exam, we should also be careful about the calculation, but let me talk about it next Wednesday. For the following Wednesday, we will practice with protein data bank to see how we can find the specific proteins from it and how we can obtain information from this database as much as possible. We will practice it together for sure on Wednesdays. Okay, guys, if you have any questions, please let me know. Otherwise, I will see you on Wednesday.